Constant versus changing acceleration. Another tricky concept. Constant acceleration versus changing acceleration. If an object has acceleration, then acceleration is either going to be changing or constant. In constant acceleration, the object's velocity changes by the same amount every second. In changing acceleration, the object's velocity changes by different amounts every second. Watch the animations on the next slide to see the difference between the constant acceleration and changing acceleration. Got it? All right, so whenever we're presented with graphs, the first thing we're going to do is look at the axes. That's the absolute first thing we have to look at. So we're looking at a velocity versus time. Velocity versus time. We see a straight line here, which means something is constant. The slope is constant. And then here we have a bend in our slope. So for this, velocity is steadily increasing. Every second that goes by, it's going 20 meters per second faster. Here, first one it goes up 40, the next one it goes up only 20 more, and then the third one it goes up 10 more, so it looks like we're slowing down. Or our acceleration is decreasing. Our acceleration is decreasing based on the charts, and what's happening to the slope? The slope is also decreasing. Velocity changes by the same amount every second. We said that already. Velocity meter rotates at a constant rate. Yes. The slope of velocity versus time is a constant. It's a straight line. Over here, we've got the velocity changing by different amounts every second. The velocity meter needle changing based on how quickly it rotates at different speeds. And then the slope of this velocity versus time is not constant. This is really important. The slope of velocity versus time graph is acceleration. This is really important. The slope of a velocity versus time graph is acceleration. Please memorize this. Please, absolutely please. We know already that the slope of a position versus time graph gives us velocity. Well, now we're going one step further and we're saying the slope of velocity versus time graph is acceleration. You have to have those facts committed to your memory. Whenever we have a fraction as an equation, I look at it as rise over run. Rise over run. That means the slope. This is my rise, this is my y-axis or dependent variable. And this is my run, or the x-axis, the independent variable. Rise on a v versus t graph. Run on a v versus t graph. Slope on a v versus t graph. Slope equals rise over run. Therefore, constant acceleration means the slope of a velocity versus time is constant. Slope of a velocity versus time graph that is constant means a constant acceleration. Notice this constant slope here. That's what I mean by constant. It's a straight line. It is not changing. That means our acceleration does not change. Our acceleration is constant. It's so important because as we go further through this unit, especially when we get to 2.3, we're going to be introduced with some equations. And those equations are only useful if we have a constant acceleration. If we don't have a constant acceleration, then we have to use calculus, which is okay, but it's a whole different tool in the toolbox. Okay. Let's test your ability to determine the directions of velocity and acceleration. In each of the following examples, you'll see a marble rolling on an incline and a motion map is also shown. For each case, pause the video and determine the direction, left or right of velocity and acceleration of the marble. Ready? Acceleration on an incline. Acceleration always points downhill. Get it? What's the direction? To the right. Notice the velocity getting bigger to the right. That's because the marble is moving to the right. What's the direction of acceleration? Are we speeding up? Yes, those velocity arrows are getting bigger, so our acceleration must be in the same direction. To the right. Acceleration has the same direction as velocity if the object is speeding up. Get it? We know we're slowing down because our velocity is getting smaller as we're going. So that means our acceleration is in the opposite direction of our velocity. Just by looking at an object going, we can determine the direction of velocity, right? It's going forward, it's going right, it's going left. Seeing the direction of acceleration is definitely more tricky because you have to ask yourself, what is this object doing? Is this thing speeding up? If so, then the tangential acceleration is in the same direction. If it is slowing down, then the tangential acceleration is in the opposite direction. Are we speeding up or slowing down? Typo. That is not to the right. Clearly, you're not looking at this wrong. That marble is going to the left. Is it speeding up or slowing down? Right? That means acceleration always points downhill on an incline. Tangential acceleration always points downhill on an incline. The magnitude or the amount of acceleration depends on how steep the ramp is. Look at the different ramps here, and you'll see the speedometers changing accordingly. Non-constant acceleration. The first 2 seconds almost have the same steepness. It's almost a straight line. Almost constant acceleration. The last second is much less steep. Acceleration, or the slope, decreases as steepness decreases, right? So our velocity is changing by a lot right here. It's picking up speed